Just like free body diagrams were essential to our ability to understand and communicate ideas about forces, electric circuit diagrams are going to be crucial to our ability to understand and communicate ideas about electric circuits. So before we get deeper into the topic of electric circuits, the first thing I want to do is make sure we know how to draw all the key elements in an electric circuit diagram so that we can communicate ideas to each other. Now, one thing that every single electric circuit is going to have is a power source of some sort. This could be a plug in the wall that you're plugging a cord into. It could be a little AA battery. It could be a solar panel. It could be one of any number of things. But every electric circuit's going to have a power source. And the symbol we'll use on our diagrams for a power source looks like this. So we have a short line and a long line, and these represent the positive and negative terminals on our power source. For example, if you remember looking at like a small AA battery, usually one end is marked positive and one end is marked negative. All power sources are like that. Now, the way that these two terminals behave is the positive terminal is essentially positively charged, and the negative terminal on the power supply is essentially negatively charged. So that means that if my circuit uses positive charges, so if these wires have positive charges in them, then this positive terminal will repel those positive charges, and they'll head out this way along the wires of the circuit away from the positive terminal. And we call that electric current. Now, if our wires or our electric circuit, instead of positive charges, has negative charges in it, they will be repelled by the negative terminal, and so they will head out this way along the electric circuit. Now, when scientists were first studying electric circuits, they didn't really know whether their charges were positive or negative. So they kind of took a stab at it, and they guessed that these metal wires they were working with had positive charges in them. So they kept talking about, they assumed that the charges were moving this way, away from the positive terminal, and they kept talking about current as heading in that direction. Many years later, when we had a better understanding of the structure of an atom, scientists realized that the charges in their currents were actually negative. So what they thought was positive charges heading to the right was actually negative charges heading to the left. So we now know that in almost all electric circuits, what we have are negatively charged electrons flowing to the left. But because so much work had been done under the assumption that these currents had positive charges flowing to the right, we still today talk about electric current as if it's imaginary positive charges and they're heading this way, away from the positive terminal. So that's a bit of history on why we draw power sources the way we do and the vocab we use around them. The function of the power source is it basically causes electric charge to flow by giving it potential energy. Now, one of the things that I find makes electric circuits tricky to understand is we can't see with our eyes what's going on inside the circuit. We see some of the effects of the circuit. We see light bulbs coming on and speakers turning on and motors moving. But what's happening inside the circuit itself, these charges flowing one way or the other, we can't see that. So that makes it, I think, difficult for students to get sort of an intuitive understanding, to really grasp what's happening with electric circuits. So what I find useful is to use an analogy, to compare electric circuits to something else that we do have a really good understanding of, where we can see what's going on, that behaves in a similar way. And the analogy I really like to use for an electric circuit is a ski hill. And the thing on a ski hill that behaves the same as a power source in an electric circuit is the chairlift. So just like a power source causes electric charges to flow by giving them potential energy, a chairlift causes skiers to move by giving them potential energy. It lifts them up to the top of the hill where they have more gravitational potential energy than they did at the beginning. So in this analogy, the charges in our electric circuit are a lot like the skiers on our ski hill. Now, the next thing we'll have in an electric circuit is we'll have some wires. And wires are pretty easy to draw. We just draw them with straight lines. You can see even in my diagram for the power source, I kind of drew some wires already, right there and right there. And the purpose of a wire in an electric circuit is to provide an easy path for charges to flow through. And the thing that's like a wire on our ski hill is a cat track. And I'll tell you why. So a cat track is very easy to ski. You don't need to turn, you don't need to have edge control. You can basically just point yourself and go as fast as you want on the track. The other reason a cat track is a lot like wires is that as charges flow down a wire, they keep their potential energy. And as skiers ski down a cat track, they tend to keep their potential energy as well. Cat tracks don't go very steeply downhill. They're normally quite flat. So you maintain a lot of height while you're skiing on one. So the power source in our electric circuit is a lot like a chairlift, and the wires in our electric circuit are a lot like cat tracks on the ski hill. The next thing we're going to see on our circuit diagrams is a symbol representing some device that's doing something. This could be a light bulb that's providing light, or it could be a motor that's spinning, or it could be a heater that's providing some heat, or it could be a speaker that's providing some sound. And one thing that all of these devices do is they will add resistance to the circuit. So what we're going to model them as is we're going to model them all as resistors. And the symbol for a resistor, for anything that adds some resistance to a circuit, looks like a wire with some squiggles in it. That's the symbol for a resistor. And what a resistor does in an electric circuit is it slows the charges down and causes them to lose potential energy. And the reason they're going to lose potential energy is because it's being converted to other forms of energy. They'll lose their potential energy and it'll be converted to light energy if this resistor is a light bulb, or it's converted to sound energy if the resistor is a speaker, or it's converted to heat energy if the resistor is a heater. Now, the thing in our ski hill analogy that acts like a resistor would be a more regular ski run. That has some more steepness to it, that maybe has some obstacles, requires you to dig in your edges and slow yourself down a little bit. So when you're going down a ski run, like I said, it's a little more steep. There's maybe some obstacles, some trees, some moguls. You're going to have to slow yourself down. You're going to have to use your edges. And this means that you'll be creating some sound energy from the scraping of your edges down the run, some heat energy from the friction between your edges and the snow. And as you're doing this, you're losing potential energy because this run is steeper than a cat track. You're constantly losing height, losing your potential energy as you go down it, just like a charge that's moving down a resistor. Another thing we'll find in a lot of our circuits is a switch. The symbol for a switch will look like this. And the idea here is we've got a wire coming along and then a wire on the other end, but they're not connected because this wire in the middle is sort of on a hinge, and that allows it to sort of flip up and down, either making a closed circuit when it's down that charges can flow through, or an open circuit when it's up that charges can't flow through. And the effect is that this switch is able to start and stop the flow of charges, or start and stop electric current. And the thing on a ski hill that serves the same purpose, in my mind, is the lift attendant. They have the power to hit a button, turn off the chairlift, and then basically all the skiers, all the charges, have to stop moving. So those are all the devices in our electric circuit that will actually affect what the circuit does. But there's two more devices I want to talk about. And these are devices that won't change what the circuit's doing, but they're used more to observe the circuit. They're used to make measurements about what the circuit is doing. And those devices are an ammeter and a voltmeter. Now, what an ammeter does is it measures electric current. And another way to think of this is it's basically counting electric charges. And the way we'll draw it in our circuit is like this. So let's say we had some device in a circuit. A little resistor, we'll draw it as here. And I wanted to measure the electric current through that device. I wanted to count how many charges were coming through that device in a given amount of time. What I would do is I would put an ammeter, which we represent as a circle with an A in it, as part of the circuit in line with that resistor. And then as charges flowed through the circuit, through this resistor, they would then be forced to go through the ammeter where it would count them and tell me how many charges, for example, were coming by every second. So the way I set this ammeter up is crucial. I have to set it up in a way so that any charges that go through my resistor also go through my ammeter. That way, when my ammeter measures current, I know I have the same current in the resistor. So this is a lot like if you had, say, a gate set up on the ski hill somewhere that counted the number of skiers going through it. And the last device I want to go over that we're going to include in some circuit diagrams is called a voltmeter, which is used to measure the difference in potential energy along one of the devices in our circuit. So let's say I have a circuit with some kind of device in it. Maybe this is a heater, maybe it's a motor, maybe it's a light bulb. But the point is, as the current coming in, the charges coming into this device will have a high potential energy, and then the charges going out the other side will have a lower potential energy. Because in the device, some of that potential energy would have been converted to heat, if this is a heater, or light, if this is a lamp, or kinetic energy, if this is a motor. So we have less potential energy coming out than coming in. And a voltmeter is used to measure that difference. And the way a voltmeter is hooked up is we sort of attach it to both ends of the circuit. Or both ends, rather, of the device where we're trying to measure the difference in potential energy. Now, I should be a little clear about something. Although there definitely is a difference in potential energy between here and here, that's not exactly what this voltmeter measures. What the voltmeter measures is the difference in something called potential, which is very similar to but slightly different from potential energy. So let's have a look at our ski hill analogy. If this little diagram of part of a circuit was actually a ski hill, this would be a skier coming along a cat track and then going down a steep run with some moguls and trees on it, and then coming out another cat track at the bottom. And they would lose potential energy from the beginning to the end of that run. And this voltmeter, I like to think of as being sort of like a tape measure that's attached or that goes from one end of the run to the other end of the run and measures not the change in potential energy, but the change in height from along one end of the run to the other. So our skiers have less height here than they did up here. That height isn't the same thing as potential energy, but they're obviously very closely related. And a voltmeter is sort of like a device that will measure that difference in height. Only in an electric circuit, we don't call it height, we call it a difference in potential. Now, but before I finish off, there's one thing that's really important to realize here, and that's the difference between how we set up an ammeter and a voltmeter. An ammeter is part of my circuit, so that any charges that are going through my circuit have to then go through my ammeter. And that's how it counts the charges and measures the current. A voltmeter, like a measuring tape, doesn't require things to go through it in order to work. The voltmeter is outside of the circuit. The charges do not go through the voltmeter in order for it to do its measurements. I can't measure the difference in height along a run by just throwing a measuring tape in the middle of the run. I have to extend the measuring tape, attach one side of it to the bottom of a run, the other side of it to the top of a run, and get my measurement that way. So ammeters are part of the circuit and voltmeters are attached outside the circuit. So those are all the fundamental circuit parts that we're going to need to be able to understand circuit diagrams in this unit. Like I said before, this stuff can feel a little non-intuitive because it's hard to see what's going on in these circuits. But hopefully this analogy with the ski hill will help a little bit in certain situations at least.